This is the last lesson of Louvain 1.1x. Only the final exam is left now. The final exam, which is worth 50% of the final grade, as much as all the homework problems put together. But be careful, you only have 2 tries for each question, unlike the homework exercises for which you had unlimited number of tries. We have covered a lot of ground in this course, and I recommend that you revisit some of the videos in previous lessons. I'm sure you will find new things and understand more by looking at them again. All the concepts in this course, we've seen them in terms of functional programming, but in fact they remain valid for all paradigms. So this is a good foundation for programming as a discipline. Let's now briefly recapitulate what we've seen. So the course is organized in 2 paths, an operations path and a data path. Operations, where we saw the kinds of things we can do, the instructions we can do, and the data structures on which we do these things. So we started in lesson 1 by looking at the basic concepts: identifier, variable, environment, scope, also by looking at the Mozart system, by getting used to the A syntax, and basically getting familiar with the approach of the course. And then in lesson 2, we looked at invariant programming. This is basically the right way to do loops. In the functional paradigm, it leads to tail recursion, and it has to do with the technique of communicating vases. So this approach is also valid for other paradigms. Then in lesson 4, we introduced higher order programming. This consists of 2 ideas, a contextual environment and procedure values. Together, they form the foundation of data abstraction, so they will be used much later on. This is sometimes called closures, procedure values with contextual environment, or lexically scoped closures. It's the same concept. And then finally, we introduce the full, complete kernel language of the functional paradigm, its instructions, its values, and in particular, procedure values and record values. So that's the operations path. In the data path, we started by talking about lists, our first recursive data structure. A data structure that is recursive is built on top of smaller versions of itself, exactly analogous to recursive functions. We showed how to define them with grammar rules, and we showed how to program with them using pattern matching. We then introduced records. This is a fundamental compound data structure of fixed size, and this is the only one that is in the kernel language. So this compound structure allows us to encode things, atoms, tuples, lists, and other data structures. So that's records. And finally, we saw trees. This is our second recursive data structure. We saw ordered binary trees. We saw search trees, how to use trees to insert, look up, and delete information as an example of goal-oriented programming. And then, at that point, we bring together all these ideas and look at what happens when our programs hit reality, when they run on real hardware. And when they run on real hardware, the important issue is performance. So, whether it's practical, our programs to run them with a practical amount of space, practical amount of time. So we introduced the notions of computational complexity, asymptotically defining the time and space usage of a programming as the size increases without limit. We also looked at Moore's law. This is a practical law of performance of real hardware. And we looked at some intrinsic limits of how far an algorithm's performance can go, the notion of NP problems, NP completeness. And then in lesson 6, kind of the crowning moment of this course is the formal semantics. We gave a complete formal semantics of programming languages, started from the kernel language, which we saw in lesson 4, and we added then the abstract machine on which the kernel language executes. So this is a formal mathematical definition of a machine, and each instruction has its own semantic rule. So this is the roadmap of Louvain 1.1x, and this leads to Louvain 1.2x. So In Louvain 1.2x, we will build on what we learned in Louvain 1.1x, and in particular, higher order programming will be the foundation of data abstraction and object-oriented programming, which we will see in Louvain 1.2x. Single assignment will be the foundation of deterministic data flow concurrency, in some sense the best model for concurrent programming, and the kernel language approach, which we used to define functional programming, we will use it in Louvain 1.2x to define all the paradigms we will see, so we will use this approach uniformly in Louvain 1.2x. So let me make a few final remarks now that we're nearing the end of the course. So first of all, I hope you enjoyed the course, despite or perhaps because of its unconventional approach and language. In fact, we don't really like to follow fashions in programming, as you have may noticed. We try to understand things as they are, and the textbook also follows this approach. So we hope that this has given you an interesting, unconventional, and clear view of programming concepts and how they fit together. The next course, Louvain 1.2x, sees many more concepts. It is every bit as rich and challenging as Louvain 1.1x, so we hope you take the plunge and continue with Louvain 1.2x.